Imagine a world where our understanding of physics was limited to the predictable motion of planets and the familiar laws of gravity. This was the scientific landscape in the early 20th century. Physicists had successfully explained many phenomena, from the falling of apples to the movement of celestial bodies, using classical physics. However, cracks began to appear in this seemingly complete picture. Scientists found that classical physics failed to explain some puzzling observations, particularly at the atomic and subatomic levels. Light, for instance, sometimes behaved like a wave and sometimes like a particle, a baffling duality that defied explanation. The stage was set for a revolution, a fundamental shift in our understanding of the universe. Little did anyone know that the year 1925 would witness the birth of a new physics, a physics that would challenge our very perception of reality. This new physics, known as quantum physics or quantum mechanics, would reveal a bizarre and counterintuitive world where energy existed in discrete packets called quanta, and particles like electrons could behave like waves, blurring the line between the observer and the observed. The year 1925 was a pivotal year for science, a year that witnessed an unprecedented outpouring of groundbreaking ideas and discoveries. It was a time when the boundaries of human knowledge were being pushed to their limits, and the scientific community was buzzing with excitement and anticipation. It was the year when the seeds of quantum physics, sown in the preceding years, blossomed into a full-fledged scientific revolution. The foundations of classical physics were being questioned, and new theories were emerging that would change our understanding of the universe forever. One of the most significant breakthroughs of 1925 was the development of matrix mechanics by a young German physicist named Werner Heisenberg. Heisenberg, who was just 23 years old at the time, was working on the problem of atomic spectra, trying to understand the behavior of electrons in atoms. Working tirelessly on the problem of atomic spectra, Heisenberg devised a novel mathematical framework that abandoned the classical notions of position and momentum. Instead of using these familiar concepts, he represented the quantities as matrices, which are mathematical arrays that could capture the strange, discontinuous nature of the quantum world. This was a radical departure from the classical view of physics, and it opened up a whole new way of thinking about the behavior of particles at the atomic level. Instead, he represented these quantities as matrices, mathematical arrays that could capture the strange, discontinuous nature of the quantum world. This new approach allowed scientists to make sense of the seemingly chaotic behavior of particles at the quantum level, and it provided a powerful new tool for understanding the fundamental nature of reality. Meanwhile, in another corner of Europe, Austrian physicist Erwin Schrödinger was hard at work on a different approach to understanding the atom. Schrödinger was inspired by the wave-particle duality of light, a concept that had been proposed by Albert Einstein and others in the early 20th century. Inspired by the wave-particle duality of light, Schrödinger developed a wave equation that described the behavior of electrons as waves. This was a completely different approach from Heisenberg's matrix mechanics, but it was equally revolutionary. Schrödinger's wave equation provided a way to calculate the energy levels and other properties of atoms and molecules, and it quickly became a cornerstone of quantum mechanics. His equation, known as the Schrödinger equation, became a cornerstone of quantum mechanics, providing a powerful tool for calculating the energy levels and other properties of atoms and molecules. It allowed scientists to make precise predictions about the behavior of particles at the quantum level, and it opened up new avenues of research in fields ranging from chemistry to materials science. These were just two of the many groundbreaking discoveries that emerged in 1925. The world of physics was abuzz with excitement and confusion as scientists grappled with the implications of these new theories. The old classical world was crumbling, and a new quantum reality was emerging from its ashes. The world of physics was abuzz with excitement and confusion as scientists grappled with the implications of these new theories. The old classical world was crumbling, and a new quantum reality was emerging from its ashes. The discoveries of 1925 laid the groundwork for the development of modern physics, and they continue to shape our understanding of the universe to this day. The old classical world was crumbling, and a new quantum reality was emerging from its ashes. The discoveries of 1925 laid the groundwork for the development of modern physics, and they continue to shape our understanding of the universe to this day. The work of Heisenberg, Schrödinger, and their contemporaries has had a profound impact on science, and it has opened up new possibilities for technology and innovation. As we look back on this remarkable year, we can see how it set the stage for the scientific revolutions that would follow, and how it continues to inspire new generations of scientists and thinkers. Amidst the flurry of discoveries in 1925, one physicist stood out as a guiding light, a visionary who helped shape the course of the quantum revolution, Niels Bohr. Based in Copenhagen, Bohr had already made significant contributions to atomic physics with his model of the atom, which proposed that electrons orbit the nucleus in specific energy levels. Bohr embraced the new quantum ideas with open arms, recognizing their potential to revolutionize our understanding of the atom. He established the Institute for Theoretical Physics in Copenhagen, which quickly became a hub for the world's leading physicists, drawn by Bohr's reputation and the exciting developments in quantum physics. At his institute, Bohr fostered an atmosphere of intense collaboration and debate. He encouraged young physicists like Heisenberg and Schrödinger to share their ideas and challenge each other's assumptions. It was within the walls of Bohr's institute that the foundations of quantum mechanics were laid. Bohr's own contributions to quantum physics were profound. He developed the concept of complementarity, which proposed that quantum objects, like electrons, could exhibit both wave-like and particle-like behavior depending on how they were measured. This idea challenged the classical notion of a single objective reality, suggesting that the act of observation played a fundamental role in shaping the quantum world. Bohr's influence extended beyond his scientific contributions. He was a mentor, a teacher, and a philosopher. His lectures were known for their depth and clarity, inspiring countless students and colleagues. Bohr's Institute was not just a place of research, it was a community. Scientists from around the world came to Copenhagen, drawn by the opportunity to work with Bohr and his team. Among them was Albert Einstein, who often visited to engage in deep discussions about the nature of reality. These discussions were legendary, often lasting late into the night. Bohr and Einstein had differing views on quantum mechanics, but their debates were always respectful and intellectually stimulating. Bohr's handwritten notes from these sessions reveal the intensity and passion of their exchanges. The library at Bohr's Institute was a treasure trove of knowledge, filled with books and papers on the latest developments in physics. It was a place where ideas were born and theories were tested. Bohr's students were among the brightest minds of their generation. He nurtured their talents, encouraging them to think critically and creatively. Many of them went on to make significant contributions to physics, carrying forward Bohr's legacy. In recognition of his groundbreaking work, Bohr received numerous awards, including the Nobel Prize in Physics in 1922. His achievements were celebrated worldwide, but Bohr remained humble, always emphasizing the collaborative nature of scientific discovery. Bohr's impact on science and humanity is immeasurable. His ideas continue to influence modern physics, and his institute remains a beacon of research and innovation. The legacy of Niels Bohr, the quantum visionary, lives on, inspiring future generations to explore the mysteries of the universe. One of the most radical and unsettling concepts to emerge from the quantum revolution was Heisenberg's uncertainty principle. This principle, formulated by Werner Heisenberg in 1927, stated that certain pairs of physical properties, such as the position and momentum of a particle, could not both be known with perfect accuracy. This was a groundbreaking departure from the classical physics that had dominated scientific thought for centuries. The more precisely one property was measured, the less precisely the other could be known. This inherent limitation was not a result of technological shortcomings, but a fundamental characteristic of the quantum realm. Heisenberg's uncertainty principle sent shockwaves through the world of physics. It was a concept so counterintuitive that it took time for even the brightest minds to fully grasp its implications. It challenged the deterministic worldview of classical physics, which assumed that the future of any system could be predicted with perfect accuracy if its initial conditions were known. Classical physics operated under the belief that the universe was like a grand clockwork mechanism where every event could be precisely calculated. In the quantum world, however, there was an inherent fuzziness, a fundamental limit to our ability to measure and predict the behavior of particles. This fuzziness was not just a minor inconvenience, but a profound shift in understanding the nature of reality. This uncertainty wasn't due to any limitations in our measuring instruments. It was an intrinsic property of the quantum world itself. The very act of measurement altered the system being observed, introducing a level of unpredictability that was previously unimaginable. The act of observing a quantum system inevitably disturbed it, making it impossible to know everything about it with certainty. This was a radical departure from the classical notion that the observer could remain separate from the observed. This profound insight had profound philosophical implications, raising questions about the nature of reality, objectivity, and the role of the observer. It suggested that the observer and the observed were inextricably linked, challenging the very foundations of how we understand the universe. Today, the uncertainty principle remains a cornerstone of quantum mechanics, influencing not just physics but also fields like philosophy, computer science, and even art. It continues to inspire and challenge us, reminding us that the universe is far more mysterious and complex than we ever imagined. As we delve deeper into the quantum world, Heisenberg's radical concept serves as a guiding light, urging us to question, explore, and embrace the unknown. The uncertainty principle is not just a scientific theory, it's a testament to the boundless curiosity and ingenuity of the human spirit.